I still have no idea how to transfer function.
You need a clicker? Huh? You need a clicker?
No.
Can you get started?
All right, sounds good. All right, everyone, we're going to get started. Thanks, Alex, for inviting me to lecture again on scientific visualization and spatial visualization topics. So today we are going to talk about the second component of the spatial visualization lectures, specifically volume rendering. Volume rendering is probably the key typical example of what I call direct visualization, what I hope other people call direct visualization too. Yeah, it's basically the idea is that we are turning samples in space into pixels, colored pixels on the screen, and blending them together in a very special way. And we have a special classification system for how to do that. So just a quick overview of what we talked about in the last spatial viz lecture. We talked about fields and grids. Fields are continuous and grids are sort of a discrete representation. We talked about unstructured and structured grids with respect to geometry of the grid. So in spatial viz or sci-viz parlance, anything that is unstructured is anything where there's no sort of nice rectilinear grid around it. So tet mesh, hex mesh, raw particles, those are all unstructured geometry. And something like a rectilinear data set or even a curvilinear data set would be structured. We also talked about direct and indirect workflows. So direct would be something like volume rendering, which we're going to talk about today. And indirect would be something like isosurface extraction, anytime you have to do some sort of filter in between the data acquisition and then the rendering. And then we talked about interpolation, and I just gave some examples about bilinear and trilinear. These are sort of basics that allow us to go from the continuous setting, so fields, to this discrete setting, grids. So today, I will talk about basics of computer graphics. Quick show of hands, who's had a computer graphics course before? Okay, about half the class. So some of this will be very, very boring for you. Quick show of hands, who has had the CS6620 ray tracing class before? Okay, a lot of this will be new. Okay. Who's had CS5600 or 5610? Yeah, that's okay. I'm going to assume everyone basically knows what rasterization is, so I might fly through those slides. We'll talk about that, we'll talk about shading, we'll talk about blending, which is sort of the key operation that makes volume rendering work. I'll talk about how we tie that together in volume rendering, how integration works. Then we'll talk about classification, transfer functions, and I'll give examples of 1D, 2D transfer functions, and some more exotic, less useful, and less seen in practice transfer functions. Reading, the assigned reading we had for today's lecture was the real-time volume graphics book from Klaus Engel and many excellent co-authors. Just look through essentially the first chapter, but also 3, 4, and 5. Those sections are also very good. They really cover things that are a little bit old now, but the fundamentals are still the same of how you would do a basic raycaster on the GPU or the CPU. So now I will talk about 3D computer graphics basics. So computer graphics is the process of converting a 3D scene or model into a 2D image, the frame buffer, via camera. And there are two principal ways of doing this. One, the most common, I guess most popular, is rasterization, which is really the process of projecting the scene and then sorting and shading a bunch of textured fragments, really think triangles, and then shading them either per pixel or in some sort of interpolated way using the bilinear interpolation idea that we had in the last lecture. And the idea here is that the camera directly transforms the primitives. It's really just a 4x4 matrix multiplication. You pair that with the Z-buffer algorithm to sort, and then you have something like Bresenham to do scan conversion from vector graphics, so triangles, into actual pixels. The cost of this is O of n with respect to the number of objects, and the APIs we have for this are things like OpenGL, WebGL in the browser, 3JS is what we used in the homework assignment last year to control WebGL. So there are lots of interfaces for how to control graphics from the browser. I'm not going to go into them too much today. We're going to talk about more fundamentals of spatial viz and specifically volume viz. Ray tracing is probably a more general algorithm. The idea here is to generate the rays from the eye, then search through the scene to find out where a primitive hits a ray, and then shade there. And that's the idea of ray casting. And ray tracing is really the same idea, except you're doing this recursively over and over until you've decided you've done enough work or you need to terminate the ray. Here the idea is that the camera defines the ray, and the primitives are always in native 3D world space coordinates. So the hardware we need for this is generally slightly different from what you'd want from rasterization, but in practice nowadays everything CPU or GPU is this sort of general purpose programmable many-core architecture either way. The cost for this is really O of log n with respect to the number of primitives, but it also depends on the size of your frame buffer. So the larger an image, the more expensive it's going to be to fill that, to ray trace it. And there's some open source and non-open source, mostly vendor-driven APIs for ray tracing, like NVIDIA Osprey, NVIDIA Optics, and of course you can write your own. And the important thing for today's lecture is that volume rendering can be implemented using either of these techniques, either a ray tracing centric approach or a rasterization centric approach. So just to give you a quick idea, this is an image that I've shown probably way too many times giving an Intel related talk. This is what you would get rasterizing a streamlined visualization and an isosurface in pair view using just the OpenGL renderer. And if you ray trace it and you add in a nice HDRI light in the background, you can get an effect like this. So it's always nice to use ray tracing if you have the option, but very often ray tracing will be a lot more expensive. So this image, I think it was at 128 samples per pixel and took several hours to production render. No, it wasn't that long. Probably several minutes to production render, whereas the rasterizer was cranking it out at multiple frames per second. So rasterization is integrated. I'm just putting these up mostly for convenience and interest. Let's see. I'm just going to show some of the simple examples of how we convert from a frame buffer into pixels. I'm sorry, from here we go. So this is really basically how Bressenham line drawing algorithm works. Looks like we have to wait for it to load. Yeah, here we go. But this is really fundamental to almost everything we're doing in graphics. We start up with our frame buffer, and Bressenham line drawing is really just drawing lines according to some implicit equation across the screen. And if you do it according to an arbitrary line, so like y equals mx plus b, you would fill it in like this. So he also talks about color channels. I'm not going to talk too much about this because actually, Alex, did you cover color theory in an earlier class? Yeah, this is probably repeating a lot of that. But rasterization is really, really doing this. It's really filling in a bunch of pixels according to a vector graphics representation of the fragment or the polygon that you have, and it's more or less doing this as quickly as it can using specialized hardware exactly for that. So I just put up these slides because I think they're probably some of the best tutorials for graphics, but I'm not going to go through them because it's, again, more of a graphics talk than what we need for Viz today. And ray tracing, the resources for this are, and if you are interested in this and you haven't taken it yet, take the 5600 and 5610 classes. And for ray tracing, take the 5620, 6620 class, and look into Osprey and Optics as NVIDIA and Intel provided vendor open source packages.
Aaron, what's the 5600 class?
That is the intro to computer graphics. So the basic computer graphics, it actually gives an overview of both rasterization and ray tracing. It's mostly for undergraduates. Yeah.
And 6610, 5610 is the interactive graphics, right?
Yes, that's right. Yeah. So that's Chuck's class. Although, who's is it
Jim's
teaching? Jim's. Oh, okay. Jim's teaching it this coming semester. Yeah, highly recommended. So Going a little bit back to visualization land, we had these sort of core elements in the VTK data model that corresponded to more often elements of a mesh or a grid. And in graphics, you have very similar concepts, except here you're more focused on what can you actually render, especially through a rasterizer. But they're very similar concepts. You have points, lines, triangle fans, triangle strips, quad strips. And when you actually render polygons, you're interested in attributes like the color, usually at each vertex, the normal, and again, these can be really the vertex or the face of a polygon. And then you have this concept of opacity, or alpha, which is very key to what we're going to be talking about today. And then finally, texture coordinates, which I would say we do not care about very much in visualization at all, unless you're doing something very specialized with the fixed function rasterization pipeline. Most of the time, texturing is something that exists really in the context of 3D rasterized graphics and 3D modeling and animation, but in Viz, we tend to think less about texture mapping. Not that we never do it, but it's much less common. So the rasterization pipeline, this is again going to be covered in most graphics classes, but I thought I'd just go over here. The idea is you start with your camera and primitives, which are really defined by the user. Then you have this transformation stage where you convert this into, via 4x4 matrix into screen space, and then you have, this is where you do the object space transformation. So applying your scene and really concepts of what you're doing in object space still. Then you have lighting and projection, and then you actually have the actual rasterization, so the Brissingham filling algorithm, then finally texturing of that. So again, this is a fill stage, and then you get an image out of it. And then in between, you have sort of programmable aspects of the pipeline. These are really part of OpenGL or DirectX. They're controlled by what the graphics hardware can do. So for example, here you have compute shaders that you can apply pretty much any stage. And then as you go further down, you have more specialized shaders at the vertex or geometry stages, and then finally the fragment. And if you wanted to just do raycasting or ray tracing, your options would really be to use the fragment shader here or the general compute shader here. So yeah, with direct visualization, with GPU raycasting would be really implemented almost exclusively in this part of the pipeline, or it would be very early on, ignoring the rest of the pipeline. So here I'm going to talk a little bit about the pinhole camera. A pinhole camera is, I'd say, a very common concept in computer graphics. The idea here is that you specify an eye position, an eye direction, an eye orientation, or commonly, if you're thinking about OpenGL, it's the glue lookat function has the origin, the direction, and the up vector. And then sometimes you have a field of view, which is the angle, between that specifies the width of the camera. And this transformation defines the world space to image space, 4x4 matrix. So in OpenGL, you would use these commands. For example, you use glue lookat, origin, direction, and up, and glue perspective with this field of view. And in 3JS, actually this is even easier, but we're not going to talk about this year because we don't have homework 6. But in short, in OpenGL, this is all pretty much straightforward. And it's also very straightforward if you look at ray tracing APIs like Osprey or Optics. You have very similar APIs for how you'd specify a pinhole camera. And what a pinhole camera lets you do is it lets you do a perspective projection where objects are closer to objects that are close to you look kind of slanted, but as you get farther away, they're they get smaller. And this is in contrast to an orthographic projection where everything ends up being more or less the same, and you have the straight lines that go on forever. That's the idea here is that we end up using pinhole cameras for almost everything we do in 3D graphics, in volume visualization or in rasterization or ray tracing of polygonal geometry. I have seen orthographic projections, but for the most part, we're doing perspective projection or pinhole cameras through a ray tracer. So, and this is what the perspective projection looks like. It's just the 4x4 matrix. The important and sometimes tricky part is this last coordinate, the homogeneous coordinate, where you're dividing by the depth. Again, this is all more or less covered in computer graphics texts, but this holds true for what we're doing in visualization too, at least if we have a rasterizer. Now for something a little bit easier than rasterization, we'll talk about ray tracing. And here you have a pipeline that's a little bit more straightforward, but with one key change. Instead of this sort of hardware-driven pipeline where you're interested in how can you transform vertices and then use Bressenham to rasterize them on the scene, you end up having these two steps, the acceleration structure and the ray traversal, which are really more or less fixed by the ray tracing APIs. So Osprey or Optics, for example, will have their own fast implementations of how to build an acceleration structure and traverse that acceleration structure. And this is true especially if you have a lot of complicated geometry, but also if you have a large volume data set and you want to decompose it into something that can be traversed efficiently and classified efficiently. So you see this a lot in Optics and Osprey, this idea of creating a volume data set, turning it into some sort of block decomposition, and then having a transfer function that classifies it. At least in Osprey, that's what the API looks like. And also, if you look at something like Images 3D, you'll probably have slightly different semantics, or slightly different implementations with the same semantics underneath for volume raycasters on the GPU like this. So yeah, the ray tracing pipeline, again, you specify the camera, you have your scene, you build the acceleration structure around the scene, you have a ray traversal algorithm followed by ray intersection of the geometric primitives, followed by shading and texturing of the actual objects that you've hit by each ray, and then each ray turns into a pixel, and then you have an image that comes out of that. And ray casting is just once through this pipeline, and ray tracing allows you to recurse from the traversal, intersection, and shading component until your ray terminates. And this is how you set up a pinhole camera in a raycaster. This is actually more or less the same code on GPU or CPU. Not quite sure why I said GPU. Oh yeah, it's because of this component. This is how you would actually get it into the fragment chamber. But this is the same code that you see in the CPU, where you have your look at an origin, so your eye position, and then you're going to do a few cross products to get your I guess UVW orthonormal frame, and then you're going to get once you normalize that, you have these U and V vectors that define basically how wide each pixel is, and then you can assemble the parametric equation for each pixel out of that. And it's really just two linear equations with respect to x and y. And that's your pinhole camera.